In this module, we're going to talk about a new concept called collision resistance, which plays an important role in providing message integrity. Our end goal is to describe a very popular MAC algorithm called HMAC that's widely used in Internet protocols. HMAC itself is built from collision-resistant hash functions. Before we do that, let's do a quick recap of where we are. In the last module, we talked about message integrity, where we said that a MAC system is secure if it is existentially unforgeable under a chosen message attack. This means that even an attacker who is given the tag on arbitrary messages of his choice cannot construct a tag for some new message. And then we showed that in fact any secure PRF immediately gives us a secure MAC. And so then we turned around and said, well, can we build secure PRFs that take large messages as inputs? And so we looked at 4 constructions. The first construction was based on CBC. When we looked at 2 variants of it, one called encrypted CBC and one called CMAC. And we said that these are commonly used with AES. In fact, in the 802.11i standard, CBC MAC is used for message integrity, in particular with the AES algorithm. We looked at another mode called NMAC, which also converts a PRF for short inputs into a PRF that's capable of taking very large messages as input. And these 2 were both sequential MACs. We then looked at a parallelizable MAC called PMAC, which again was able to convert a PRF for small inputs into a PRF for very large inputs, but it did so in a parallel fashion, so a multiprocessor system would be more efficient with PMAC than, say, with CBC MAC. All 3 of these built a MAC for large messages by constructing a PRF for large messages. And then we looked at the Carter-Wagman MAC, which actually is not a PRF, it's a randomized MAC, so a single message could actually have many, many different valid tags, and therefore Carter-Wagman MAC is actually not a PRF. And if you remember, the Carter-Wagman MAC was built by, first of all, taking the bulk message and hashing it down to a small tag using a fast one-time MAC, and then encrypting that tag using a PRF. The benefit of the Carter-Wagman MAC was that, as we said, the hashing of the bulk message is done using a fast one-time MAC. And then in this module, we're going to construct MACs from a new concept called collision resistance. And so the first thing we're going to do is construct collision-resistant hash functions. So let's first of all start by defining what does it mean for a hash function to be collision-resistant. So think of a hash function from some message space to a tag space T, and you should be thinking of the message space as much, much bigger than the tag space. So the messages could be gigabytes long, but the tags would only be like 160 bits. Now, a collision for the function h is a pair of messages m0, m1 that happen to be distinct. However, when you apply the function h to them, you end up with the same output. So the image you should have in your mind is essentially there are 2 inputs, m0 and m1. They belong to this gigantic message space. However, when we apply the hash function to them, they happen to collide and they both map to the same output in the tag space. Now, we say that the function h is collision resistant if it's hard to find collisions for this function. Now, this should seem a little bit counterintuitive because we know that the output space is tiny compared to the input space. So by the pigeonhole principle, there must be lots and lots and lots of messages that map to the same output, just because there isn't enough space in the output space to accommodate all the messages without collisions. And so we know that there are lots of collisions, and the question is there an efficient algorithm that finds any such collisions explicitly? So we say that the function is collision resistant if for all explicit efficient algorithms A, and these algorithms are not able to print a collision for the function h. Okay, and as usual, we'll define the advantage as the probability that the algorithm A is able to output a collision. Now, I'm not going to formalize the term explicit here. All I'll say is that it's not enough to just say that an algorithm exists, an algorithm that simply prints a collision, because we know many collisions exist. What we actually want is an explicit algorithm that we can actually write down and run on a computer to generate these collisions. There are ways to formalize that, but I'm not going to do that here. Now, a classic example of a collision-resistant hash function is SHA-256, which happens to output 256 bits, but can take arbitrarily large inputs. For example, it can take gigabytes and gigabytes of data, and it'll map it all to 256 bits, and yet nobody knows how to find collisions for this particular function. So just to show you that this concept of collision resistance is very useful, let's see a very quick application for it. In particular, let's see how we can trivially build a MAC given a collision-resistant hash function. So suppose we have a MAC for short messages. So you should be thinking something like AES, which can MAC 16-byte messages. And then suppose we have a hash function, a collision-resistant hash function, from large message space that contains gigabyte messages into our small message space, say into 16-byte outputs. Then basically we can define a new MAC, let's call it I big, which happens to be macking large messages, and we'll define it simply by applying the small mac to the output of the hash function. And how do we verify a mac? Well, basically, given a tag, we verify it by rehashing the given message and then checking that small mac actually verifies under the given tag. Okay, so this is a very simple way to show you how collision resistance can take a primitive that's built for small inputs and expand it into a primitive that's built for very large inputs. And in fact, we're going to see this not just for Macs. Later on, when we talk about digital signatures, we're going to do the same thing. We're going to build a digital signature scheme for small inputs, and then we're going to use collision resistance to expand the input space and make it as large as we want. So the security theorem basically is in some sense trivial here. Basically, it says if the underlying MAC is secure and H is collision resistant, then the combination, which can actually MAC large messages, is also a secure MAC. And as a quick example, let's apply this to AES. So let's use the one example that we mentioned, SHA-256. So in this case, SHA-256 outputs 256-bit outputs, which is 32 bytes. So we have to build a MAC that can MAC 32-byte messages. And the way we could do that is basically by applying the 16-byte AES, plugging it into a 2-block CBC. A 2-block CBC would expand AES from a PRF on 16 bytes to a PRF on 32 bytes, and then take the output of SHA-256 and plug it into this 2-block CBC based on AES. And then we get a very, very simple MAC, which is secure, assuming AES is a PRF and SHA-256 is collision resistant. So one thing I wanted to point out is that in fact collision resistance is necessary for this construction to work. So in fact, collision resistance is not just a made-up term. Collision resistance really is kind of the essence of why this combined MAC is secure. And so let's just assume for a minute that the function H, the hash function we're using, is not collision resistant. In other words, there is an algorithm that can find two distinct messages that happen to map to the same output. In this case, the combined MAC is not going to be secure because what the adversary can do is simply use the chosen message attack to get a tag for M0 and then output M1, comma, that tag as a forgery. And indeed, T is a valid MAC for M1 because H of M1 happens to be equal to H of M0. And so in doing so, just with a one chosen message attack, the attacker was able to break this combined MAC simply because the hash function was not collision resistant. So it should be, again, I want to emphasize that if someone advertised even one collision for SHA-256, two messages, just one pair of messages that happen to have the same output under SHA-256, that would already make this construction insecure, because an attacker could then ask for the tag on one message, and in doing so, he would obtain the tag on the other message as well. And that would count as an existential forgery. Okay, so already we see that collision resistance is a very useful primitive in that it lets us expand the input space of cryptographic primitives. I want to show you one more application where collision resistance is directly used for message integrity. Imagine again we have files that we want to protect. Let's imagine these files are actually software packages that we want to install on our system. So here are 3 different software packages. Maybe one is GCC, one is Emacs, and another one is, VI. Now the user wants to download the software package, and he wants to make sure that he really did get a version of the package that he downloaded, and it's not some version that the attacker tampered with and modified its content. So what he could do is basically refer to a read-only public space that's relatively small. All it has to do is hold small hashes of these software packages. So there isn't a lot of space needed here. The only requirement is that this space is read-only. In other words, the attacker cannot modify the hashes stored in this space. And then once he consults this public space, he can very easily compute the hash of a package that he downloaded, compare it to the value in the public space, and if the two match, then he knows that the version of the package he downloaded is in fact a correct one. Why is that true? Well, because the function H is collision resistant, the attacker cannot find an F1 hat that would have the same hash as F1. And as a result, the attacker cannot modify F1 without being detected, because there's no way that the hash of his F1 hat would map to the value that's stored in the public space. So the reason I brought up this example is I wanted to contrast this with the Mac example. We kind of saw a similar situation with Macs. In the Mac example, we needed a secret key to verify the individual file tags. but we didn't need a resource that was a read-only public space. With collision-resistant hashes, we kind of get the exact complement, where in fact we don't need a key to verify. Anyone can verify. You don't need a secret key for it. However, now all of a sudden we need this extra resource, which is some space that the attacker cannot modify. And in fact, later on, we're going to see that with digital signatures, we can kind of get to the best of both worlds, where we have both public verifiability and we don't need a read-only space. But so far, with either MACs or collision resistance, we can have one, but not the other. So I'll tell you that in fact this kind of scheme is very popular. In fact, Linux distributions often use public spaces where they advertise hashes of their software packages, and anyone can make sure that they downloaded the right software package before installing it on their computer. So this is in fact something that's used quite extensively in the real world. Okay, so in the next segment we'll talk about generic attack on collision resistance, and then we'll go ahead and build collision resistant hash functions. The next thing I want to do is show you a general attack on collision resistant hash functions. If you remember when we talked about block ciphers, we saw a general attack on block ciphers which we called exhaustive search, and that attack forced the key size for a block cipher to be 128 bits or more. Similarly, on collision resistance, there's a general attack called the birthday attack, which forces the output of a collision-resistant hash functions to be more than a certain bound. And so let me show you the attack, and then we'll see what those bounds come out to be. So here's a general attack that can work on arbitrary collision-resistant hash functions. So here we have our collision-resistant hash function, supposedly. Let's suppose that it outputs n bit values. In other words, the output space is roughly of size 2 to the n. Now the message space is going to be much, much larger than n bits. Let's just say that the messages that are being hashed are, say, 100 times n bits. I want to show you an algorithm that can find a collision for this hash function h in time roughly 2 to the n over 2. Okay, so roughly the square root of the size of the output space. So here's how the algorithm is going to work. What we'll do is we'll choose random 2 to the n over 2 messages in our message space. Let's call them m1 to m2 to the n over 2. Now, because the messages themselves are much bigger than n bits, they're 100 times n bits, it's very likely that all these messages are distinct. So they'll be distinct with high probability. But for each one of these messages, we're going to apply the hash function and obtain a tag t sub I. So this is, of course, the t sub i's are n-bit long strings. And now we're going to look for a collision among the t sub i's. In other words, we're going to find an I and a j such that t sub I equals to t sub j. And once we've done that, we've basically found a collision because, as we said, with very high probability mi is not equal to mj, but the hash of mi is equal to the hash of mj, and therefore we found a collision on the function h. Now, if it so happens that we look through all 2 to the n over 2 t sub i's and we don't find the collision, we go back to step 1 and try another set of 2 to the n over 2 messages. So the question is, how well will this work? In other words, how many times do we have to iterate this process until we actually find the collision? And I want to show you that, in fact, the number of iterations is going to be very, very small, which means that this algorithm will find the collision in time that's roughly proportional to 2 to the n over 2. So to analyze this type of attack, I have to tell you a little bit about the birthday paradox. I imagine some of you have already heard of the birthday paradox. Here stated as a theorem, and I want to prove it to you because everybody should see a proof of the birthday paradox at least once in their lives. So here it is. So imagine we have n random variables, r1 to rn, in the interval 1 to b. And the only thing I'm going to assume about them is that they're actually independent of one another. That's crucial, that these n samples, r1 to n to rn, in this interval are independent of one another. And they also happen to be distributed identically. So for example, they might all be uniform in the interval 1 to b, but again, these would be independently uniform variables. Now, it so happens that if we set n to be about the square root of b, in other words, if we sample roughly square root of b samples from the interval 1 to b, to be precise, it's 1.2 times the square root of b, then the probability that 2 of those samples will be the same is at least a half. Okay, and then it turns out, in fact, the uniform distribution is the worst case for the birthday paradox. In other words, if the distribution from which the RIs are sampled from is non-uniform, then in fact fewer than 1.2 times square root of b samples are needed. The uniform distribution is the worst case. So we're going to prove this for the uniform distribution, and that basically just also proves it for all other distributions. But the proof that I want to show you here will hold just for the uniform distribution. Okay, so let's do the proof. It's actually not difficult at all. So we're asking, what is the probability that there exists an I that's not equal to j, such that Ri is equal to Rj? Well, let's negate that. So that's basically 1 minus the probability that for all I not equal to j, we have that Ri is not equal to Rj. This basically means that no collision occurred among the n samples that we chose. Well, let's try to write this out more precisely. Well, we're going to write this as 1 minus. And now when we choose R1, basically it's the first one we choose, so it's not going to collide with anything. But now let's look at what happens when we choose R2. When we choose R2, let me ask you, what is the probability that R2 does not collide with R1? Well, R1 takes one slot, so there are b minus 1 slots that if R2 falls into, it's not going to collide with R1. So in other words, the probability that R2 does not collide with R1 is b minus 1 slots divided by all b possible slots. Similarly, when we pick R3, what is the probability that R3 does not collide with either R1 or R2? Again, R1 and R2 take up 2 slots, and so there are b minus 2 slots that remain for R3. If it falls into either one of those b minus 2 slots, it's not going to collide with either R1 or R2. So I imagine you see the pattern now. So R4, its probability of not colliding with R1, R2, or R3 is b minus 3 over b, and so on and so forth until we get to the very last Rn, and the probability that Rn does not collide with the previous Ris, well, there are n minus 1 slots taken up by the previous Ris. So if Rn falls into any of the remaining b minus n plus 1 slots, it's not going to collide with any of the previous R1 to Rn minus 1. Now you notice the reason I was able to multiply all these probabilities is exactly because the Ris are all independent of one another. So it's crucial for the step that the Ris are independent. So let me rewrite this expression a little bit. Let me write it as 1 minus the product of I goes from 1 to n minus 1 of 1 minus I over b. Okay, all I did is I just rewrote this as a big product as opposed to writing the terms individually. So now I'm going to use a standard inequality that says that for any positive x, 1 minus x is less than e to the minus x. And that's actually easy to see because e to the minus x, if you look at its Taylor expansion, is 1 minus x plus x squared over 2 minus and so on and so forth. And so you can see that we're basically ignoring this latter part of the Taylor expansion, which happens to be positive, and as a result, the left side here is going to be smaller than the right-hand side. Okay, so let's plug this inequality in, and what do we get? We get that this is greater than 1 minus the product of I goes from 1 to n minus 1 of e to the minus I over b. Okay, I simply plugged in x equals I over b for each one of those terms. Now the nice thing about exponentials is that we multiply them, the exponents add. As a result, this is simply equal to 1 minus e to the power of, here, let me take the 1 over b out of the parentheses, sum of I goes from 1 to n minus 1 of I. Okay, so all I did is I took the minus 1 over b out of the parentheses, and we're left with a simple sum of 1 to n minus 1. And so the sum of the integers from 1 to n minus 1 is simply n times n minus 1 over 2, which I can bound by n squared over 2. And so really what I get at the end here is 1 minus e to the power of minus n squared over 2b. Okay, I literally bounded this sum here by n squared over 2. Okay, very good. Now, so what do we know about n squared over 2b? Well, we can derive exactly what n squared over 2b is from the relationship here. So if you think about it, let's look at n squared over 2. Well, n squared over 2 is 1.2 squared over 2. 1.2 squared is 1.44. Divided by 2 is 0.72 times the square root of b squared, which is b. Okay, so n squared over 2 is 0.72b, and as a result, n squared over 2b is just 0.72. So we get 1 minus e to the power of minus 0.72. Well, so now you just plug this into your calculator and you get 0.53, which as far as I know is always bigger than a half. So this proves the birthday paradox, and you notice it was crucial to assume that the samples are independent of one another. We only proved it for the uniform distribution, but as I said, it's actually fairly easy to argue now that any distribution that's away from the uniform distribution will satisfy this with even a lower bound. So if you have 1.2 square root of b, the theorem will certainly hold for non-uniform distributions. The reason it's called a paradox is because it's very paradoxical that the square root function grows very slowly. In particular, if you try to apply this to birth dates, so let's assume that we have a number of people in a room, and let's assume that their birth dates are independent of one another and are uniform in the interval 1 to 365, then what the birthday paradox says is that we need roughly 1.2 times square root of 365, which I believe is something like 23, which says we need roughly 23 people in a room, and then with probability 1/2, 2 of them will actually have the same birthday. The reason it's called a paradox is because the number 23 seems really small to people, and yet by this theorem that we just proved, with probability 1/2, there will be 2 people with the same birthday. By the way, the intuition for why this fact is true is because really what the collision is counting is it's looking at all possible pairs of people, and if you have a square root of b people, then there are square root of b squared pairs, roughly, which is roughly b pairs total, and so it's very likely that each pair collides with probability 1 over b, and if you have b pairs, it's likely that one of the pairs will collide. So hopefully this gives you intuition for where the square root comes from. It's basically from the fact that if you have n people in a room, there are n squared possible pairs. I should say, by the way, that even though the birthday paradox is often applied to birth dates are actually not uniform at all. If you actually look at the birth dates of people, you see that there's a very clear bias towards being born in September, and for some bizarre reason there's also a bias towards being born on a Tuesday. And so when we apply the birthday paradox to birthdays, in fact the actual bound is going to be smaller than 1 minus 2 square root of b, because we said that for non-uniform distributions you need even fewer samples before you get a collision. So let me show you a graph of the birthday paradox. It's quite interesting how it behaves. So here I set b to be 1,000,000. In other words, we're picking random uniform samples in the range 1 to 1,000,000. And the x-axis here is the number of samples that we're picking, and the y-axis is the probability that we get a collision among those n samples. So we see that the probability of 1/2 happens around 1.2 square root of b, roughly 1200, 1.2 square root of b. And you see that if we look at exactly square root of b, the probability for a collision is around 0.4 or 0.41. And you notice the probability goes up to 1 extremely fast. For example, already at roughly 2 square root of b, the probability of a collision is already 90%. Similarly, when we go below square root of b, the probability of a collision very, very quickly drops to 0. Okay, so there's kind of a threshold phenomena around square root of b, where the probability for a collision goes to 1 very quickly above square root of b, and drops to 0 very quickly below square root of b. So now we can analyze our attack algorithm. So let me remind you, here we chose 2 to the n over 2 random elements in the message space. We hashed them. And so we started off with a random distribution in the message space. After we hashed them, we end up with some distribution. This distribution over tags might not be uniform, but we don't care. The point is that all these tags, t1 to t2 to the n over 2, are independent of one another. And as a result, if we choose 2 to the n over 2 or 1.2 to the n over 2 tags, the probability that a collision will exist is roughly 1/2. So let me ask you then, in that case, how many times do we have to iterate this algorithm before we actually find a collision? Well, so since each iteration is going to find a collision with probability 1/2, we have to iterate about 2 times in expectation, and as a result, the running time of this algorithm is basically 2 to the n over 2 evaluations of the hash functions. Okay, so notice also this algorithm takes a lot of space, but we're going to ignore the space issue, and we're just going to focus on the running time. Okay, so this is kind of cool. This says that if your hash function outputs n-bit outputs, there will always be an attack algorithm that runs in time 2 to the n over 2. So for example, if we output 128-bit outputs, then a collision could be found in time 2 to the 64, which is not considered sufficiently secure. Okay, so this is why collision-resistant hash functions generally are not going to output 128 bits. So let me show you some examples. The first 3 are actually federal standards, SHA-1, SHA-256, and SHA-512. And the fourth one is an example from the designers of AES called Whirlpool. And so you can see SHA-1 outputs 160 bits, and as a result there's a generic attack on it that runs in time 2 to the 80. SHA-256 outputs 256 bits, so the generic attack will run in time 2 to the 128, and so on and so forth. I also listed the speeds of these algorithms, and you notice that the bigger the block size, actually the slower the algorithm is, and so there's a performance penalty, but nevertheless there's quite a bit of benefit in terms of security. Now you notice the SHA function is actually grayed out. The SHA function, although nobody has found collisions for SHA-1 yet, it's still recommended that in new projects and hopefully in programming projects in this class, you don't use SHA-1, instead use SHA-256. And in particular, there's actually a theoretical collision finder on SHA-1 that works in time 2 to the 51. So it's probably just a matter of time until finally someone finds a collision for SHA-1 and just kills altogether. But the current advice is SHA-1 is still a collision-resistant hash function because nobody has found collisions for it, but it's probably just a matter of time, just a few months or a few years until a collision is found. And as a result, in new products and new projects, SHA-1 should not be used and only use SHA-256, or if you want to be even more cautious, then use SHA-512. So this is the end of this segment, and now we're going to turn to building collision-resistant hash functions. So now we're going to look at a very general paradigm called the Merkle-Damgard paradigm that's used for constructing collision-resistant hash functions. Before we do that, let me just remind you what our goals are. So as usual, we say that H is a hash function that maps some large message space into a small tag space. And we say that a collision for the hash function is basically a pair of distinct messages that happen to map to the same value under this hash function. And our goal is to build collision-resistant hash functions, namely functions where it's hard to find even a single collision. Even though we know many collisions exist, no efficient algorithm can even output a single collision. So we're going to construct these hash functions, these collision-resistant hash functions, in 2 steps. The first step, which we're going to do in this segment, is to show that if you give me a collision-resistant hash function for short messages, we can extend it and build a collision-resistant hash function for much longer messages. In the next segment, we'll actually build collision-resistant hash functions for short messages. Okay, so let's look at the construction. The construction is actually very general, and in fact, all collision-resistant hash functions follow this paradigm. It's actually a very elegant paradigm, and let me show you how it works. So here we have our function h, which we're going to assume is a collision-resistant hash function for small size inputs. So the way we're going to use this little function h, this h is sometimes called a compression function, is we're going to take a big message m and break this message into blocks, and then we use a fixed value called the IV. Here in this case the IV is fixed forever, and it's basically embedded in the code and in the standards. It's just a fixed IV that's part of the definition of the function. And then what we do is we apply the small compression function h to the first message block along with this IV. What comes out of that is what's called a chaining variable that's going to be fed into the next compression function, which compresses the next block along with the previous chaining variable, and out comes the next chaining variable, and the next message block is compressed, and so on and so forth, until we reach the final message block. And in the final message block, the one special thing that we do is we must append this padding block, this PB, which stands for padding block, and I'll explain what the padding block is in just a second. But after we append the padding block, we again compress the last chaining variable with the last message block, and the output of that is the actual output of the hash function. So just to summarize, in symbols, we have this compression function that maps elements in T. This is the output of the hash function, plus message blocks. This X corresponds to message blocks, and outputs the next chaining variable. So as I said, this is what the compression functions do. And then from this compression function, we're able to build a hash function for large inputs, namely inputs in the space X to some power of L, namely up to L blocks of X. And of course, these are variable length, so we can have different length messages that are being given as input to this function h. And what comes out of it is basically a tag in the tag space. So the only thing that's left to define is the padding block. And so the padding block actually is very important, as we're going to see in just a minute. What it is basically, well, it's a sequence of 1, 0, 0, 0, just to denote the end of the actual message block. And then the most important part of the padding block is that we encode the message length in this padding block. And the message length field is basically fixed to be 64 bits. So in all the SHA hash functions, the maximum message length is 2 to the 64 minus 1. So in fact, the message length fits into a 64-bit block. And an upper bound of 2 to the 64 minus 1 bits on the message length is actually sufficiently long to handle all the messages we're going to throw at it. Okay, so that's the padding block. And of course, the question is, what do we do if the last block really is a multiple of the compression function block length? Where are we going to fit the padding block? And the answer, as usual, is basically if there's no space for the padding block in the last block of the message, then we're going to have to add another dummy block and stick the padding block in there, and of course put the 1000 in the right place. Okay, so the point is it's very, very important that the padding block contains the message length, as we'll see in just a minute. So this is the Merkle-Damgard construction. The last piece of terminology I'll say is that we have these chaining variables. So h0 is the initial value, h1, h2, h3, up to h4, which is the actual final output of this hash function. So as I said, all standard hash functions follow this paradigm for constructing a collision-resistant hash function from a compression function. The reason this paradigm is so popular is because of the following theorem, which says basically that if the little compression function is collision resistant, then the big Merkle-Damgard hash function is also collision resistant. So in other words, if we're going to build collision resistant functions for large inputs, all we have to do is just build compression functions that are collision resistant. So let's prove this theorem. It's an elegant proof and it's not too difficult. So the way we're going to prove it is using the contrapositive. That is, if you can find me a collision on the big hash function, then we're going to deduce a collision on the little compression function. Therefore, if little h is collision resistant, so will be the big H. So suppose you give me a collision on the big compression function, namely two distinct messages m and m prime that happen to hash to the same output, we're going to use m and m prime to build a collision on the little compression function. So the first thing is we have to remember how the Merkle-Damgard construction works, and in particular, let's assign names to the chaining variables when we hash m versus when we hash m prime. So here are the chaining variables that come up when we hash the message capital M. So h0 is the fixed IV that starts the whole process. h1 would be the result of hashing the first message block with the IV, and so on and so forth, until h sub t plus 1 is the final chaining variable, which is the final output of the Merkle-Damgard chain. And then similarly for m prime, let's define h0 prime to be the first chaining variable, h1 prime to be the result after compressing the first message block of m prime, and so on and so forth, up until we get to h prime of r plus 1, which is the final hash of the message m prime. Now you notice the length of the messages m and m prime don't have to be the same. In particular, m has length t, whereas m prime has length r. Now because the collision occurred, we know that these two values here are the same. H of m is equal to h of m prime. In other words, the last chaining variables are actually equal to one another. So now let's look carefully how ht plus 1 and h prime r plus 1 were calculated. Well, ht plus 1 is calculated as the compression function applied to the previous chaining variable along with the last message block of m, including the padding block. You notice here I'm assuming that the padding block fits with the last message block of m. Even if the last padding block is in its own block, it's not going to make any difference. So for simplicity, let's assume that the padding block fits with the last message block of capital M. So by hashing the last message block with the padding block and the last chaining variable, we obtain ht plus 1. And similarly, the same thing happens with m prime. By hashing the last message block, the last chaining variable, we obtain h prime r plus 1. And we know that since these two values are equal, all of a sudden we have a candidate collision for the compression function. Here, let me circle the candidate collision. This is one part of it, and this is the other part of it. Okay, so we have an equality between two arguments given to the compression function that happen to produce the same value. The only way we would not get a collision is if the arguments happen to be the same. In other words, what we're saying here is if the arguments to the compression function are distinct, then we get a collision for little h. So let's write it out more precisely. So if ht is not equal to h prime r, or mt is not equal to m prime r, or the padding blocks are distinct, then we have a collision for the compression function h, and we're done. We're done and we can stop. So the only way we need to continue is if this three-way disjunction doesn't hold. So what does it mean that this junction doesn't hold? Well, so the only reason we need to continue is if the second to last chaining variables are equal, the last blocks of the messages are equal, and the two padding blocks are equal. So what does it mean that the two padding blocks are equal? Remember that the message lengths were encoded in the padding block. So in particular, this means that the length of m and the length of m prime is the same, namely that t is equal to r. So from now on, I can assume t is equal to r, and whenever I wrote r, I'm just going to write t. But now we can apply exactly the same argument to the second to last chaining variables. In other words, how was ht computed? Well, ht is computed by hashing the previous chaining variable, namely ht minus 1, with the second to last message block. And similarly, ht prime was computed, you notice I replaced r by t, so ht prime was computed by hashing the previous chaining variable along with the second to last message block of m prime. And because these two are equal, now we get another candidate collision for the compression function. In other words, if ht minus 1 is not equal to ht minus 1 prime, or mt minus 1 is not equal to m prime t minus 1, then basically we have a collision for h, and we can stop. We're done. So now the only case when we need to continue is if this condition over here doesn't hold, namely, so let's suppose that ht minus 1 is equal to h prime t minus 1, and we already know that, let's see, so mt is equal to mt prime, and mt minus 1 is equal to mt minus 1 prime. Suppose it so happens that these two condition holds. Well, you can see that now we can continue to iterate. In other words, we can now apply exactly the same argument to ht minus 1 and ht minus 1 prime. And so iterating this again and again, we can iterate all the way to the beginning of the message, iterate to the beginning of the message, and one of two things must hold. Either we find a collision for the compression function, or it so happens that all the message blocks of m and m prime are the same. In other words, for all I, mi is equal to mi prime. But this means, because the messages, we already proved the messages are the same length, this means that m is actually equal to m prime. But then this contradicts the fact that you gave me a collision to begin with. So in other words, this condition over here can't actually happen because it contradicts the fact that m and m prime are actually a collision for the big Merkle-Damgard function, capital H. And as a result, this means that we have to find a collision for the compression function, so that as we work our way from the end of the message all the way to the beginning, at some point we must find the collision for little h. Okay, so this basically completes the proof of the theorem, so I can put a little QED block here. So basically what this proves is that if the little compression function h is collision resistant, then the big Merkle-Damgard function, capital H, must also be collision resistant. So again, the reason why people like this construction is it shows that to construct big hash functions, it suffices to construct just compression functions for small inputs. And we're going to do that in the next segment. So our goal for this segment is to build secure compression functions. So compression functions that are collision resistant. So just to remind you where we are, we looked at this Merkle-Damgard construction, which takes a little compression function and makes and builds from it a hash function for much, much larger inputs. And we proved this Q theorem that says that, in fact, if the little compression function h is collision resistant, then plugging it into the Merkle-Damgard construction gives us a collision resistant hash function for larger inputs. So now in this segment, our goal is basically to build a compression function that is collision resistant. So we're going to see a couple of constructions. And so the first question that comes to mind is, well, can we build compression functions from primitives that we already have? In particular, we spent a lot of work to build block ciphers. And the question is, can we build compression functions from block ciphers? And the answer is yes. And let me show you how to do it. So assume we have a certain block cipher. Here it operates on n-bit blocks. So the input is in n bits, output is n bits. And then there's this classic construction called the Davies-Mayer construction, which I wrote down in symbols here. Basically says that what you would do is, given the message block and the chaining variable, all we do is we encrypt the chaining variable using the message block as a key, and then we kind of do one more XOR on the output. So this might seem a little bizarre, because remember, the message block is something that's completely under the control of the adversary. He's trying to find a collision, so he can choose the message blocks however he wants. And yet we're using this message block as a key into a block cipher. But nevertheless, we can argue that this construction, at least when E is what's called an ideal cipher, we can argue that this construction, in fact, is as collision resistant as possible. So let me state the theorem. The theorem states that, as I said, if E is an ideal block cipher, meaning that it's a random collection of k random permutations from 0, 1 to the n to 0, 1 to the n, then under that assumption that E is an ideal block cipher, in fact, finding a collision for this compression function h takes time 2 to the n over 2. In particular, we can show that anyone who's finding collisions has to evaluate the encryption-decryption functions at least 2 to the n over 2 times. And if you think about what that means, since the output of this compression function is only n bits long, we know that there's always a generic birthday attack that finds collisions in time 2 to the n over 2. So basically this theorem says that this collision-resistant function is as collision-resistant as possible. We can find the collision in time 2 to the n over 2 using the birthday attack, but there is no algorithm that will do better than 2 to the n over 2. So Davies-Mayer is actually a very common compression function used in collision-resistant hashing. In fact, the SHA functions all use Davies-Mayer. It turns out there's something special about the Davies-Mayer construction that makes it collision-resistant. If you just try to guess a construction, very likely you'll end up with something that's not collision-resistant. And so let me ask you the following puzzle. Suppose we actually define the compression function as follows. Namely, all we do is we encrypt the chaining variable h using the current message block as the key. So the difference is that we dropped this XOR h in Davies-Mayer, we simply ignored it. So it's not there. And the puzzle for you is show me that this compression function then is actually not collision resistant. So let's see. So we're trying to build a collision, namely a distinct pair of hm and h prime m prime that happen to collide under this little function h. And my question to you is, how would you do it? So I'm already going to tell you that you're going to choose h, m, and m prime arbitrarily. The only requirement is that m and m prime are distinct. And then my question is, how would you construct an h prime that would cause a collision to pop out? So the answer is the first choice, and the easy way to see it is if we apply the encryption function using m prime to both sides, then we get that this is basically e of m prime applied to h prime, right? This is what we get by applying encryption using m prime to the left-hand side. And if we apply encryption using m prime to the right-hand side, the decryption operator cancels out, and we simply are left with the encryption of m comma h, which is exactly the collision that we wanted to find. So there, you can see that it's basically by using the decryption function d, it's very easy to build collisions for this compression function. Now I should tell you that in fact Davies-Mayer is not unique. There are other ways to build collision-resistant compression functions from block ciphers. For example, here's a method called Miyaguchi-Pernille. Miyaguchi-Pernille actually is used in Whirlpool hash function that we saw earlier. Here's another method that happens to result in a collision-resistant compression function. And there are 12 variants like this, playing with XORs and placing the variables in different slots that will actually give a collision-resistant mechanism. But there are also many, many variants of this, like we saw in the previous puzzle, that are not collision-resistant. So here's another example that's not collision-resistant, and I'm going to leave it as a homework problem to figure out a collision for this construction. So now basically we have all the ingredients to describe the SHA-256 hash function. I'll tell you that it's a Merkle-Damgard construction exactly as the one that we saw before. It uses a Davies-Mayer compression function. And so the only question is, what's the underlying block cipher for Davies-Mayer? And that block cipher is called SHA-CAL2. And I'll just tell you its parameters. It uses a 512-bit key. And remember, the key is taken from the message block. So this is really what the message block is. And it so happens to be 512 bits, which means that SHA-256 will process its input message 512 bits at a time. And then the block size for this block cipher is 256 bits, and these are the chaining variables. So this would be hi-1, and this would be a successive chaining variable. So now you have a complete understanding of how SHA-256 works, modulo this block cipher SHA-CAL2 that I'm not going to describe here. So as I said, one class of compression functions is built from block ciphers. It turns out there's another class of compression functions that's built using hard problems for number theory, and I want to very briefly show you one example. And we call these compression functions provable because if you can find a collision on this compression function, then you're going to be able to solve a very hard number theoretic problem, which is believed to be intractable, and as a result, if the number theoretic problem is intractable, the resulting compression function is provably collision resistant. So here's how this compression function works. Basically, we're going to choose a large prime p, so this is a gigantic prime, something like 700 digits, 2,000 bits, and then we're going to choose two random values u and v between 1 and p. And now let's define the compression function as follows. It takes two numbers between 0 and p minus 1, and it's going to output one number between 0 and p minus 1. So its compression ratio is 2 to 1. Yeah, it takes two numbers and outputs one number in the range 0 to p minus 1. And it does it basically by computing this double exponentiation. It computes u to the h times v to the n. And the theorem, which right now I'm just going to state as a fact, this fact actually turns out to be fairly straightforward to prove, and we're going to do it later on when we get to the number theoretic part of the course. The fact is that if you can find a collision for this compression function, then you can solve a standard hard problem in number theory called a discrete log problem. Everyone believes discrete log is hard, and as a result, this compression function is provably collision resistant. So you might ask me, why do people not use this compression function in practice? Why would we not use this for SHA-256? And the answer is that this gives very slow performance in comparison to what you get from a block cipher, so this is not really used for any compression functions. However, if for some reason you really only want to, say, MAC or sign just one long message and you have a whole day to do it, then certainly you can use this type of compression function, and even though it's slow, you'll get something that's provably collision resistant. Okay, so that's the end of this segment, and now we're finally ready to talk about HMAC, which we're going to do in the next segments. So now that we understand what collision-resistant hash functions are and we know how to construct them, we're ready to describe a very popular MAC called HMAC. So let me remind you what the Merkle-Damgard construction is. Basically, we have a small compression function h from which we build a large hash function which is collision-resistant, assuming the compression function is collision-resistant. The question we're going to ask this segment is, can we use the large hash function to construct a MAC directly without having to rely on a PRF? So here's the first thing that comes to mind. Suppose I give you a Merkle-Damgard hash function. So you notice it hashes large messages into small digests. And we want to convert that directly into a MAC. So the first thing that comes to mind is, well, why don't we just hash the concatenation of the MAC key along with the message that we're trying to MAC? And it turns out this is completely insecure. And so let me ask you why this is insecure. The answer is the standard extension attack, and if you think back to the Merkle-Damgard construction, you realize that if I tell you the tag for a particular message, in other words, I tell you the value at this point, it's very easy for the attacker to just add another block and then compute one more application of the compression function h, and now they will be able to get the tag for the original message, concatenated the padding block, concatenated their word w that they added themselves, and as a result, this is an existential forgery. Yeah, so basically this is exactly what we get here, where after concatenating the padding block, the attacker can actually concatenate whatever he wants, and he would get the tag on this combined message. So this is totally insecure, and I cannot tell you how many products have actually made this mistake, where they assume that this is a secure MAC. This is completely insecure and should never, ever, ever be used. Instead, there's a standardized method to convert a collision-resistant hash function into a MAC, and that method is called HMAC. So, in particular, we could use the SHA-256 hash function to build this MAC. The output is going to be 256 bits, and in fact, HMAC is believed to be a pseudo-random function. So, in fact, out of SHA-256, we get a pseudo-random function that outputs 256-bit outputs. So let me show you the construction. Here's the construction in symbols, and it works as follows. First, we take our key k, and we concatenate what's called an internal pad to it, an I-pad to it. This makes it into one block of the Merkle-Damgard construction. So for example, this would be 512 bits in the case of SHA-256. We prepend this to the message m, and then we hash. Now this by itself, we just said, is completely insecure. However, what HMAC does in addition, it takes the output, which is 256 bits, it prepends to that the key again, XORed with what's called the outer pad, the O pad. This also becomes 512 bits. It's one block. And then it hashes the combination of these two to finally obtain the resulting tag on the message M. So it's more, rather than looking at this in symbols, it's more instructive to look at HMAC in pictures. And so you can see here are the two keys, K XOR inner pad, which is then fed into the Merkle-Damgard chain, and then the resulting output of this chain is fed into another Merkle-Damgard chain, and finally the final output is produced. Okay, so this is how HMAC works in pictures. And now I want to argue that we've already seen something very similar to this. In particular, if you can think of the compression function h as a PRF, where the key is the top input, then what we're actually doing here is we're evaluating this PRF h at a fixed IV, and therefore the result here is a random value which we're going to call K1. And then we apply the Merkle-Damgard chain, and we can do the same thing on the outer pad. If you think of little h as a PRF, where the key is the upper input, again, we're applying this PRF using a different key to a fixed value IV, and as a result, we're going to get another random value, K2. So now when we compute HMAC using these keys K1 and K2, this should actually look very familiar. This is basically NMAC. It's identical to NMAC that we discussed in a previous segment. And notice, to argue that this is an NMAC construction, we have to assume that the compression function, little h, is a PRF where the key is actually the lower input to the function. Now let me say that these pads, the I pad and the O pad, these are fixed constants that are specified in the HMAC standard. So these are literally just 512-bit constants that never change. And so when we go back to look at the complete HMAC construction, you realize that the main difference between this and NMAC is that these keys here, since they're dependent, you notice they're both just the same key XORed with different constants. Essentially, the keys K1 and K2 are also somewhat dependent because they're computed by applying a PRF to the same fixed value, namely IV, but with dependent keys. And so to argue that K1 and K2 are pseudo-random and independent of one another, one has to argue that the compression function not only is a PRF where when the input, the top input, is the key input, but it's also a PRF when dependent keys are used. But under those assumptions, basically the exact same analysis as NMAC would apply to HMAC, and we would get a security argument that HMAC is a secure MAC. And so, as I said, HMAC can be proven secure under these PRF assumptions about the compression function H. The security bounds are just as they are for NMAC. In other words, you should not have to change the key as long as the number of messages you're macking is smaller than the size of the output tag to the 1/2. But for HMAC SHA-256, the output space is 2 to the 256. Square root of that would put us at 2 to the 128, which means that basically you can use HMAC SHA-256 for as many outputs as you want, and you'll always maintain security. And as a last point about HMAC, I'll tell you that TLS standard actually requires that one support HMAC SHA-196, which means HMAC built from the SHA-1 function and truncated to 96 bits. SHA-1, remember, outputs 160 bits, and we truncated to the most significant 96 bits. Now you might be wondering, remember we said before that SHA-1 is no longer considered a secure hash function, so how come we're using SHA-1 in HMAC? Well, it turns out it's actually fine because HMAC, the analysis of HMAC, doesn't need SHA-1 to be collision resistant. All it needs is that the compression function of SHA-1 be a PRF when either input is allowed to be the key. And as far as we know, that's still correct for the underlying compression function for SHA-1. Even though it might not be collision resistant, as far as we know, it's still fine to use it inside of HMAC. So this is the end of our discussion of HMAC, and in the next segment we're going to look at timing attacks on HMAC. In the last segment in this module, I want to show you a general attack that affects many implementations of MAC algorithms, and there's a nice lesson to be learned from an attack like this. So let's look at a particular implementation of HMAC verification. This happens to be an implementation from the Keysar library that happens to be written in Python. So here's the code that's used to verify a tag generated by HMAC. This code is actually simplified. I just wanted to kind of simplify it as much as I can to get the point across. So basically what the inputs are, the key, the message, and the tag bytes. The way we verify it is we recompute the HMAC on the message, and then we compare, say, the resulting 16 bytes to the actual given signature bytes. So this looks perfectly fine. In fact, anyone might implement it like this, and in fact, many people have implemented it like this. The problem is that if you look at how the comparison is done, the comparison, as you might expect, is done byte by byte. There's a loop inside of the Python interpreter that loops over all 16 bytes, and it so happens that the first time it finds an inequality, the loop terminates and says the strings are not equal. And the fact that the comparator exits when the first inequality is found introduces a significant timing attack on this library. So let me show you how one might attack it. So imagine you're the attacker and you have a message M for which you want to obtain a valid tag. Now your goal is to attack a server that has an HMAC secret key stored in it, and the server exposes an interface that basically takes message MAC pairs, checks that the MAC is valid. If the MAC is valid, it does something with the message, and if the MAC is not valid, it says reject. Okay, it sends back to the originator the message reject. So now this attacker has an opportunity to basically submit lots of message tag pairs and see if it can deduce the tag for the particular message for which it wants a tag. And here's how we might use the broken implementation from the previous slide to do just that. So what the attacker is going to do is submit many message tag queries where the message is always the same, but with the tag he's going to experiment with lots and lots and lots of different tags. So in the first query, what he's going to do is just submit a random tag along with the target message. And he's going to measure how long the server took to respond. The next query that he's going to submit is he's going to try all possible first bytes for the tag. So let me explain what I mean by that. So the remaining bytes of the tag that he submits are just arbitrary. It doesn't really matter what they are. But for the first byte, what he'll do is he'll submit a tag starting with the byte 0. And then he's going to see whether the server took a little bit longer to verify the tag than before. If the server took exactly the same amount of time to verify the tag as in step 1, then he's going to try again, this time with byte set to 1. If still the server responded very quickly, he's going to try with a byte set to 2. If the server responded quickly, he's going to try with a byte set to 3, and so on, until finally, let's say when the byte is set to 3, the server takes a little bit longer to respond. What that means is actually when it did the comparison between the correct MAC and the MAC submitted by the attacker, the two matched on this byte, and the rejection happened on the second byte. Aha, so now the attacker knows that the first byte of the tag is set to 3, and now he can mount exactly the same attack on the second byte. So here, it's going to submit a tag where the second byte, here, let me use a different color. So it's going to submit a tag when the second byte is set to 0, and it's going to measure whether this took a little bit longer than in step 2. If not, he's going to change this to be set to 1, and he's going to measure if the server's response time is a little longer than before. Eventually, let's say when he sets this to, I don't know, when the byte is set to 53, say, all of a sudden the server takes a little bit longer to respond, which means that now the comparator matched on the first 2 bytes, and now the attacker learned that the first 2 bytes of the MAC are 3 and 53, and now he can move on and do the exact same thing on the third byte, and then on the fourth byte, and so on and so forth, until finally the server says, yes, I accept, you actually gave me the right MAC, and then it will go ahead and act on this bogus message that the attacker supplied. So this is a beautiful example of how a timing attack can reveal the value of a MAC, the correct value of the MAC, kind of byte by byte, until eventually the attacker obtains all the correct bytes of the tag, and then he's able to fool the server into accepting this message tag pair. The reason I like this example is this is a perfectly reasonable way of implementing a MAC verification routine, and yet if you write it this way, it'll be completely broken. So what do? So let me show you 2 defenses. The first defense, I'll write it again in Python, is as follows. And in fact, the Keysar library exactly implemented this defense. This code is actually taken out of the updated version of the library. The first thing we do is we test if the signature bytes submitted by the attacker are of the correct length. Say for HMAC, this would be, say, 96 bits or 128 bits. And if not, we reject that as an invalid MAC. But now if the signature bytes really do have the correct length, what we do is we implement our own comparator that always takes the same amount of time to compare the 2 strings. So in particular, this uses the zip function in Python, which will essentially, if you are giving it 2 16-byte strings, it will create 16 pairs of bytes. So it will just create a list of 16 elements where each element is a pair of bytes, one taken from the left and one taken from the right. And then you loop through this list of pairs. You compute the XOR of the first pair and you OR that into the result. Then you compute the XOR of the second pair and you OR that into the result. And you notice that if at any point in this loop 2 bytes happen to be not equal, then the XOR will evaluate to something that's non-zero, and therefore when we OR it into the result will also become non-zero, and then we'll return false at the end of the comparison. So the point here is that now the comparator always takes the same amount of time. Even if it finds a difference in byte number 3, it will continue running down both strings until the very end, and only then will it return the result. So now the timing attack supposedly is impossible. However, this can be quite problematic because compilers try to be too helpful here. So an optimizing compiler might look at this code and say, hey, wait a minute, I can actually improve this code by making the for loop end as soon as an incompatible set of bytes is discovered. And so now optimizing compiler could be your kind of Achilles heel when it comes to making programs always take the same amount of time. And so a different defense, which is not as widely implemented, is to try and hide from the adversary what strings are actually being compared. So let me show you what I mean by that. So again, here we have our verification algorithm. So it takes as inputs a key, a message, and a candidate MAC from the adversary. And then the way we do the comparison is we first of all compute the correct MAC on the message, but then instead of directly comparing the MAC and the signature bytes from the adversary, what we're going to do is we're going to hash one more time. So we compute a hash here of the MAC, we compute a hash of the signature bytes. Of course, if these two happen to be the same, then the resulting HMACs will also be the same, so the comparison will actually succeed. But the point is now, if sig bytes happen to equal MAC on the first byte but not on the remaining bytes, then when we do this additional hash layer, it's likely that the two resulting values are completely different, and as a result, the byte-by-byte comparator will just output on the first iteration. The point here is that the adversary doesn't actually know what strings are being compared, and as a result, he can't mount the timing attack that we discussed earlier. Okay, so this is another defense. At least now you're not at the mercy of an optimizing compiler. The main lesson from all of this is that you realize that people who even are experts at implementing crypto libraries get this stuff wrong. And they write code that works perfectly fine and yet is completely vulnerable to a timing attack that completely undo all security of the system. So the lesson here is, of course, you should not be inventing your own crypto, but you shouldn't even be implementing your own crypto because most likely it'll be vulnerable to these side channel attacks. Just use the standard libraries like OpenSSL. Kezar is actually a fine library to use that would reduce the chances that you're vulnerable to these types of attacks.